Welcome to From Zero to Knowledge, an explainer series brought to you by House of ZK. I'm Ashley, and I'm joined today by Vanishree. And we've talked a lot about how zero knowledge proofs work and how they've evolved over time, but all these explanations involve a lot of terms that can be confusing if you've never heard them before. So, Vanishree, I'm hoping that you can give a little more in-depth explanation to some of the vocabulary we've talked about today.
Awesome. For sure. So, let's start with constraints. I slipped that word in one of the previous videos. So, what is a constraint? We recall that we start with a computation, that we start with some representation of a computation, and then we need to go to the world where we need to take this computation to a different representation that proof systems can understand. And the way proof systems can understand a computation is through this set of constraints, a bunch of constraints. So it can be that a number should be between this and this. That's a constraint. Another constraint can be that this third number has to be a divisor of these two numbers. I'm just giving some random examples. So you have this bunch of constraints, and that can put together can represent a correct computation of something, right? So that's constraints. That's a word. It just is. It is just what it says. It's a constraint on how the numbers are related, and it represents a part of the computation, and all these constraints put together represents the entirety of the computation. So that is one word. Okay. And we have circuits. A circuit is a set of constraints put together.
Oh, okay. So simple enough. So you design your parameters and all of them together are your circuits. Like, gotcha.
For a computation, you can have a circuit, right? And then we talked about ZKVMs. We talked about ZKVMs as a way where a developer doesn't need to learn a new language. But how does it really work? Why shouldn't a developer learn a new language? But developers have different computations, so they have different crossed programs, let's say. But there is this ZKVM that can understand all these programs. Yes. Why? Because think of ZKVM as a circuit for your CPU, right? Your CPU, you take your computer can run various programs, right? You can run a calculator, you can do gaming, you can run a browser, etc. It can do a lot of computations that is one single CPU. If you ZKify that CPU itself, it can take multiple programs and run it.
Okay, right. Okay.
So that's how you bring that universality to ZKVMs while people not having to worry about learning a new language. And this ZKVM can target they can target these languages which people are familiar with.
I see. So you can translate these for you, basically. That's right.
Right. So that is ZKVM. I was a little imprecise in how I explained it, but this is the amount that one needs to know to embrace ZKVM as far as the understanding is concerned. And then we talked about a proof market. We talked about a proof market when we were talking about proof generation. Why proof markets are important is because proof generation can be resource intensive, and it can be a problematic aspect of your ZK stack for someone who is trying to embrace ZK, for a developer who is trying to embrace ZK. So proof markets try to take away the headache of figuring out the infrastructure needed for proof generation, be it a small early stage project or be it a large project. There is another word that tends to get used interchangeably with the proof market, and it's a prover network. It's a network of machines that are that together build this infrastructure to generate proofs. And another concept that it's kind of a narrative that became popular in the ZK world, and it's called client-side proving. And the idea is the following, right? Imagine you are proving something. There are two situations, possible situations. One situation where you don't have anything secret. Another situation you do have something secret. So in the first case, where you're not using the zero knowledge proof part of it, you're only using the soundness part or the succinctness part of it. And in the second case, where you actually need the zero knowledge property of it. So in the case where you do need the zero knowledge property of it, for example, in ZK identity, where you're going to prove your age limit without revealing your date of birth, for example, where there you're using the zero knowledge property of zero knowledge proofs. And when such is the case, it is very hard, it's not straightforward to imagine you delegating your proving task to a proof market. Because in proof market, you have this demand and supply, and on the supply side, there are these random GPUs or CPUs with some machines, and people are running those machines. You cannot just give all your secret information to a random person so that they can generate proofs, because this information has your secret information. So in this world, you're a client. That is why client-side proving became popular, where a client is generating the proof. Now you have to think through resource requirements. This client can be a phone. This client can be a laptop. It can actually be an old Nokia phone from a not so developed country, right? People are still using these old phones. So resource requirements in this case, client-side proving, it's a special kind of situation where resource requirements are hugely important. And there are these special proof systems that are built to try to make it easy to generate proofs on a client. And we at Fermah are working on a technology, on a protocol, where client-side proving is not even necessary. So consider this an announcement of an announcement that is coming. But I think whenever you have a problem, you want an architectural solution. You don't want to make things faster, easier. You want to shift the way you're doing things, where if you have made it a little bit faster, a little bit easier, a little bit less memory requiring, but then you have to then cater to another country where the phones have even less memory, right? You don't want a solution like that. You want to completely break this off, shift into a world where you can actually still delegate. Your architecture allows for delegation so that you can cater to the entire world, no constraints. This is the world that Fermah is envisioning, and we are working on a solution there. More will come later. So yeah, but still I wanted to highlight this notion of client-side proving, because it can be a recurrent phrase that it's used. And any questions so far, Ashley?
Yeah, so you're working on a way to kind of solve the resource constraint issue at the root level versus like treating the symptoms.
Exactly. It's correctly said. We talked about the notion of trusted setup ceremony. Just to reiterate, in the context of terminology, all proof systems need setup. Some of them need a trusted setup. Some of them don't need a trusted setup. When you need a trusted setup where there is some secret involved in that setup parameter, you run the ceremony because there is no one trusted person, right? And you do it in a collaborative manner. It is called the multi-party computation protocol. It again is a terminology. It's worth writing here. multi-party computation protocol, and you run a multi-party computation protocol, and that protocol in this case is called a trusted setup ceremony, and what it outputs is trusted. Let's just call it. It outputs the so-called setup or the setup parameters. So, any questions so far, Question?
So can we talk a little bit more about the trusted setup ceremony? I'm a little confused. All I'm thinking about are like a group of people standing around taking an oath. And I feel like I need it to be a little bit more concrete.
That's a great question. I think. Right. So, let's see here. So trusted setup ceremony. Think of it looking like this. There is a parameter D, and there is parameter tau. I'm using tau because this is again a typical way we represent the secret. So this D everybody knows. Okay. This tau is secret that we are trying to generate. So let's say there is God, and God will choose tau. You trust God. God outputs this. They call this a big T. God tells everybody, this is the parameter you need to use. Okay, that's not the situation we are in. How do we generate this? Right? We generate this through a trusted setup ceremony as follows. Let's say there are 3 people. Party 1, party 2, party 3. Okay. Party 1 says, I will contribute my secret. Party 2 says, I will contribute my secret. Party 3 says, I will contribute my secret. They all have their own secret round numbers. Okay, this needs to be random. I have my randomness. This person has its own randomness. This person has their own randomness. Now, what we do is the first person computes G to the tau 1 and calls it T1, sends it to everybody. Person 2 says computes T1 to the tau 1. T1 to the tau 2. And this actually is G to the tau 1 multiplied by tau 2, right? And then call this T2. This person publishes T2. Gives it to everyone. Person 3 computes T2 to the power of tau 3. So what is this? G to the power of tau 1, tau 2, tau 3. Correct? Yes. Now, if you deem tau as tau 1 multiplied by tau 2 multiplied by tau 3, call this T3. This is T3. G to the tau is actually T3. I see. Okay.
That makes a lot more sense. Now, each of these people have contributed. So they all have like a little piece of the trust to come up with the secret. Okay.
And here at what we have pushed under the rug is this fact that given G to the something that is random, you need G from a special set. It's called this problem. This problem is called discrete log problem, where you actually don't know what this is. If you see T, and if you know G, you don't know what tau is. This is discrete log problem, and we make use of that the hardness of this problem in building this protocol. So that's getting a little bit more into the math, but the takeaway here, actually, I think, is how do you get together as in a ceremony, as in a protocol where you're going to build something where it has a secret, and no one single one of us know what the secret is. Tau is equal to tau 1 multiplied by tau 2 multiplied by tau 3. Nobody knows what that is. Nobody knows anything about it because it has this tau and tau2. You actually have jumbled it completely using this new fresh randomness, and it's completely random now. Tau is random. I don't know what tau1 multiplied by tau2 is, so I don't know what tau is. But we have come together to build this setup parameter in a collaborative manner. Wow. I gave a very simple explanation of how this setup parameter to look like. It looks a little bit more complex than this. Think of it as g to the tau, g to the so let me write here. The parameter instead in reality can look like g to the tau, and also there is d to the tau square, and also a bunch more things. But all this can be computed in a similar manner. So that's how this setup parameter can look like, and that's how you compute.
Perfect. So this is a great application for a world where we don't have a trusted source, which is all but 3. That's right. Are there any other applications that we should get into right now that you're really excited about?
Applications of zero knowledge proofs in general?
Yeah.
Oh yes, sure. I think that's right. So applications of zero knowledge proofs. I'm just so excited about so many of them, and I'll tell you 2 of my favorites. One is because so let's just use all the space to specify those 2 applications. One is ZK identity. Let's start with this one because we kind of talked about it. The other one is called ZK TLS. So ZK ID. So here the idea is that you are building a distributed identity, and you are using the power of zero knowledge truths to hide the unnecessary aspects of your identity when an application only needs a part of your identity. For example, you go to a bar, you need not have to show your entire driver's license to the bouncer. You only say that you're over 21 years of age with the proof, and you can do it with ZKID. And Wolg is a amazing project that is working on something like this. And then another application that I'm super bullish about is ZKTLS. I actually worked on one of the first versions of ZKTLS protocols back when I was working on the Mina protocol many years ago. And the idea is very, very powerful. Let's see.
Let's start with ZKTLS.
Okay. Cool. So here is another application of ZK that I'm super excited about because it's extremely powerful. What it does is you can prove anything about your online activity on Web3 on Web2. Sorry, you can prove any communication that has happened on HTTPS using ZKTLS. So here is a specific example, specific situation where ZKTLS can be useful. Imagine you going to apply for a loan, and you need to prove that you have a certain credit health. And let's say you want to prove that your credit score is over 800, right? What is one way? What is the current way? You fill up your form, let's say on a PDF, and write your social security number, send it over email, stays in it stays in some database. Hopefully it's somehow secured, and even if it is secured, it's a great enticing place for a hacker to go and hack, because it's a treasure trove of so much high value information. And year over year, billions of dollars are lost in not only these banks trying to secure such a database, but also in recovering from hacks that happen year after year, and in recovering from the reputation loss that they've had in those hacks. So how can CKTLS help here? The idea is that instead of you writing that down, social security number down and sending it around without knowing where all it'll touch, instead of that, you can just get a proof that you logged into one of those credit bureau websites. You checked your credit score. This is the credit score as attested by that credit bureau, and you give that proof. Your social security number hasn't gone outside of your world, your space at all. You've just given a proof. They have gotten just the information that they needed, nothing more. Right? CKTLS enables that. I really like this example because it tells you how to save billions of dollars. Like, right? So I think these two. It's great that you brought up the topic of applications, because these two are terminologies that are used in the CK space. Also, so they're great to know in this overarching theme of terminologies. Knowledge. I'm going to write them down over here.
You can erase maybe this part. That's right.
So let's expand these two. So ZK stands for, as we know, zero knowledge. And let's go for snark. So S is for succinct. It says that your proof is small. N is for non-interactive. There is no interaction between the prover and the rectifier. This is an argument. You should write this terminal of knowledge. Argument of knowledge. Not to worry about what that means. To keep this at an intuitive level. And here, T here means transparent, because there is no need for trusted.
All right, so the last two we have are zero knowledge and soundness, which we've talked about a lot. Zero knowledge is that ability to keep something secret, right? And then the soundness is how reliable it is that I would be able to catch someone in a lie.
That's right. Awesome. This is, I think there's a lot more terms, elliptic curves. There are more mathematical underlying terms that people might come across, but I think we want to limit the terminologies here to what is required for a developer to start embracing ZK. I think this in my view is a perfect set.
Awesome. Well, it's perfectly doable. Thank you so much. Thank you. In this episode, we went through a lot of the terms that you need to kind of get started, and we'll look forward to seeing you in the next one.